Very exciting title. Okay, we have 20 more seconds. I guess we have everyone. Okay, so let's get started. Welcome everyone to this special seminar of the Theoretical Computational Biophysics Group. Today, I'm very pleased to introduce Dr. Wang from Department of Physics of Chinese University in Hong Kong. So Yi is actually one of us. She was actually a graduate student here with late Klaus Schulten. And during the same time I was here working with Klaus, he was here. So by way of introduction, she got her initial degree from China in biology and computer science, and then came here to do a PhD in biophysics, which she did here, and then moved on to the group of Andy McCamon at UCSD for a postdoc before going back to Hong Kong and starting a faculty position where she is currently a professor in the physics department. So as I was telling you, Yi was a graduate student here, and I was counting how many papers we had together. She had 14 papers together, 12 of them during her PhD work. So students, listen. This can happen actually, so I'm very proud of that. So she was obviously working on membrane proteins when she was here, but since she moved on, she started working on a variety of systems using simulations, including nanomaterials, interaction with nanomaterials and biological systems, and so on and so forth. And she's going to tell us a little bit more about her work today. Thank you very much.
Thank you
for coming this way. So by the way, so many people are still coming back from BPS, and many of them are sick, unfortunately. So be careful about BPS people. Don't say that. Excellent. Yeah,
Okay, thank you. Thank you very much. It's truly wonderful to be able to come back. This is where it all started, and I'm so grateful for having the opportunity to visit Madagascar, and I had a great time talking to some of the folks here this morning, and I've been taking notes, learned quite a lot. So I'm going to use the next 40 minutes or so to tell you a bit about what we have been doing. Right. So having a root from this group, naturally, so it's a membrane systems that we started working with. So this is the these are some of the simulations that we started working before, and to continue work on after I joined the Chinese University of Hong Kong in 2012, right? So on the left, as you can see, these are permeability calculations. So we have a few projects in collaboration with Chris Cholic and also J.C. Gumbert. So we study how small molecules get across the lipid membranes, and we vary, for instance, the lipid composition, including cholesterol, and at a later work, even the mammalian membrane model that we built based on a coarse-grained model from Martini. So that's part of the membrane systems, and in the middle is a fluorescent dye that you're looking at. So this is called VF dye. It's one of the projects that I started when I was a postdoc with Andy McCamon, and I was collaborating with then postdoc Ivan Miller of Berger, right? And he later on moved to Berkeley, and so this is the dye that we work on. So basically, it's a fluorescent small molecule sensor, and the way that it works is that it's operating via the so-called photo-induced electron transfer. So basically, it's designed such that its little tail buried inside the bilayer is an electron donor, and it can donate an electron to the top fluorescing head. Okay, so basically, this is the head that is both a fluorophore and also an electron acceptor. Okay, so basically, once you shine light on them, then the electron transfer can occur, and that competes with fluorescence. And this is basically how the molecule becomes a voltage sensor, because the electron transfer is subject to the transmembrane potential. So basically, if you align it with the transmembrane potential, you promote the electron transfer and therefore quench the fluorescence. So based on that, we can sense the transmembrane potential, and we did the calculation initially, or plain empty simulations initially, just to investigate how they orient. Because as you can probably imagine, the more straight up they are, the better sensitivity they have. Whereas if you're completely 90 degrees lie down, then you lose the sensitivity. So we basically tried to model a few different types of these molecules and see which one is more sensitive.
Can we interrupt for a question? So the lipids look,
Oh, yeah,
that's the effect of averaging?
yes.
Okay.
Just
Okay.
smoothed out.
Yeah,
So
but
the-
your fluorescent molecule is not
Yeah.
affected much. Okay, interesting.
Right, yeah, so this is purely just so it raise the jumping of the molecules. Yeah, so the lipid
Okay,
have been
I see.
smoothed out. Right, so as a more recent continuation, we actually have employed a set of rather complex free energy calculation scheme, as you can see, the thermodynamic cycle, to determine what is the partition free energy of the dye molecule between lipid and water. And this is such that we can also have an idea of how likely or how much they like the membrane environment. Because presumably the more you partition, the higher the signal, and therefore the greater the signal to noise ratio. So this type of scheme actually comes from the set of scheme that Maru and also later Chipotle and also J.C. Gumbert, they worked a lot on protein ligand and protein binding for energy calculations. So basically left those and applied it on this system. So, right, so expanding on that, we also recently been collaborating with a group at Hong Kong University to study how another group of fluorescent molecules get inside the membrane. So this is basically a set of membrane systems that we worked on, and expanding on that. So actually shortly after I joined my university, I started collaborating with a colleague who works on nanoparticles, okay, and in particular nanoparticle membrane interactions. So this is basically how we got started, and later on we expanded our calculations to other systems at the so-called material cell interface or / nanomaterial cell interface. So so we have recently even worked on some inorganic systems, and also we have been collaborating with people to study how coacellate, the PEITA coacellate can achieve the wet adhesion property. Okay, so I will tell you a little bit more about the first project before I move on to the topic of hydrogel today. Okay, so this is the first collaboration that I had after I joined the physics department at CUHK. So this is Professor Chen Li at our department. Okay, so this system is basically her system that works, as a sensor, okay, or a other type of probe molecules of the cellular environment. So the idea is that you can manufacture these literally these are nanoscale diamonds, so AKA nanodiamonds. You can manufacture them and then feed them into cells. And if they can get inside the cell, and then they can be utilized for various functions, sensors primarily, okay. But what they found was that, quite interestingly, depending on the morphology, that is the shape of the nanodiamonds, they can end up having different fate. So manufactured by default, these nanodiamonds are very prickly or very sharp. Okay, so because they're one of the ways to manufacture them is detonation. Okay, it's a very violent process. So they would naturally be very sharp. And if that's the case, what they found is that they get endocytosed, so they get inside the cell, and then they can somehow break the endosome and get out of the endosome. Okay, whereas if you feed the cell with the traditional silicon dioxide round particles, you don't see that, and you get inside into endosomes, and eventually many of them would come out through exocytosis. All right, so of course they each have their utility, but if the cytosol is where you'd like to be, then maybe this is a alternative or interesting way of getting there, okay, to break the endosome. So our job was to understand the morphology dependent cellular fate of the nanodiamonds. So we did a number of different works on this, and the first one started with all atom simulations. Okay, so we basically built a nanodiamond model, like literally, and I will
Yeah.
get there. Okay,
Yeah,
so let me continue this. So our first study was actually sort of very straightforward in the sense that, all right, ecomorphology is what experiments found to be important. Let's build nanodiamonds with different shapes and then try to see how they interact with the lipid membrane. So this is all atom simulation. And then indeed, in this first work, we could see that shape is important naturally. If you are sharp enough, then you can easily anchor into the membrane versus if you're very round and smooth, you can best adhere to it. Okay, but admittedly, this study is rather different in length scale from the experiments. So our sharp and smooth are basically all sharp on the experimental length scale because this curvature is still very high, okay, compared with what we had in experiments. So later on, we tried something else, but before that, so this comes to the question from Taras and Imad. So basically, how did we model the surface? So we realized that there's actually very little guidance when it comes to modeling of this type of nanomaterial because for proteins, or other typically modeled biomolecules, we tend to have a reasonably good knowledge of what their, say, protonation states should be, or we have a good set of rules to estimate or predict that if we don't have the exact information. But for nanoparticles, one of the few pieces of information that we can get is the so-called zeta potential. So this is a very common experimental measurement. You would just put your particle in solution and then see how much apparent charges they carry. And you plug in the equations, you get the so-called zeta potential. Okay, so we thought, can we use that information and try to improve our modeling process in particular to give us some guidance as to how many charged groups or how dense the charged groups are on the surface of the nanoparticles. So for that, we actually built upon the idea from this work of Rich Faster and Maru, who basically did similar calculations for ionic lipids to parameterize the ionic lipids, to improve the parameter. So the idea is that we need a link between the actual charge on the surface and the apparent charge, which gives the zeta potential. So so we basically did that, and then that's improved our parameterization. But that's, again, not really enough because at that length scale, like I said, our smooth nanoparticles are only relatively smooth and they're still very sharp on the experimental length scale. So next we asked, like, can we go to the experimental scale? So for that, we really have to go beyond empty simulation. So this work is actually continuum modeling. So we basically resorted to elastic theory. And in this case, membranes are treated as an infinitely thin sheet with various modulus, bending modulus, stretch modulus. And in this particular case, because we want to study how they are broken, there is actually an extra line tension term entering. And that basically gives us the total energy function of the system. And then we can, the idea is actually pretty straightforward. We can, scan how favorable nanoparticles get interacting or get contact with the membrane. So there is an adhesion stress. So you have a fight between adhesion and membrane deformation in both bending, stretching, or pore formations form. So I won't go into the details. The bottom line is that from this study, we can actually say quantitatively under what conditions the poration, so basically spontaneously breaking the membrane, could happen. And we say that, and then we found that the condition for that to happen is that you not only have to be sharp enough, you actually have to have a reasonably large surface that can provide the driving force, the adhesion, favorable adhesion that would want your nanoparticle to get in contact with the membrane in the first place. And then you have a chance to porate the membrane. Okay, so that's a brief sort of history of what we have been doing. So that's sort of like a review of how we went from empty simulations of biomolecules alone to interacting with molecules. So now the story that I'm actually going to focus on today is a sort of expansion that we did in recent years. So this is in collaboration with another group who was at CUHK when we started this collaboration, but he later on moved to South China University of Technology. So Professor Li Mingbian. Okay, so the motivation of this study is this. Okay, so cells are actually intimately regulated by their extracellular matrix environment. So this is a prominent example where you can see that depending on how soft or how hard, basically the elasticity of the ECM, stem cells can become neurons, muscles, or bones. Okay. Now the question is, if you culture cells in vitro, okay, can we design materials that mimic to some degree the properties of the ECM? And one of the most important properties we want to mimic is the adaptability. So basically, if a cell would like to grow in the actual ECM, the cell can poke a little finger, say in the case of Philopodia, a bundle of actin filaments, and then we can easily do so and modify the extracellular matrix. But in the in hydrogel materials, okay, so how do we do that? Well, there has been a class of hydrogel materials that can do that is enzyme degradable. So basically, they can be degraded as the cell secretes enzymes. But there are certain limitations associated with that. And so the hydrogel materials that our collaborator developed, it's called supramolecular hydrogel that is based on host guest binding. Okay, so host guest is a very well established chemical system where you have non-covalent interactions, okay, between a host molecule, which is typically a sugar ring. It could be 6 members, 8 members. So in our case, it's a 7-member beta-cyclodextrin sugar ring. Okay, that's our host. And guest, there can be hundreds of different guests with different properties, thermodynamics and kinetics. Perhaps the most famous one is so-called adamantane. Okay, or ADA short here. So this is like literally a little unit of the diamond. Okay, so this cage, it's very hydrophobic, and it would go inside this ring. Okay, and what's interesting is now depending on the property, in particular depending on the kinetic property of this host gas binding, our cells could have very different behaviors in the resulting hydrogel. Okay, so the whole point of this project is to try to understand or provide a mechanism for such difference. So let me go back and briefly introduce a little bit about how the hydrogel is made. Okay, so the hydrogel is basically made from polymers. Okay, so each polymer is a hyaluronic acid chain or HA chain. That's the green chain here. And on top of these chains, we could decorate them with gas molecules. So in this case, we can decorate them with ADA, or we can decorate with different gas molecules. So our study is primarily focused on these 2 different gases. One is ADA, which is a fast on, fast off gas. And the other is cholic acid or Ca, which is a slow on, slow off gas. Okay, so ADA is fast on, so its K on is 10 to the 8th order. Inverse mole, inverse second. So this is about the diffusion limit. So it doesn't get any faster than this, any much faster. So the diffusion limit is about 10 to the 8th to 10 to the 9th. Okay, so this is basically means that they encounter, they bind. Okay, so that's basically what diffusion limit implies.
With the host, binding to the host.
Yes, binding to the host.
Okay.
So adamantane and beta-cyclodextrin.
Yeah, okay.
Right. So whereas the Ca is slow on, slow off.
Okay.
So there's thermodynamic property. It's not too different. So it is different. It's about 1 order of magnitude difference in KEQ. Okay. But their kinetics, their K on and K off are orders of magnitude apart. Okay. So the way that they're manufactured is that the HA chains are decorated with these different guests, and then we just mix these decorated HA chains in solution. They are solution initially, okay? And then you throw in these host molecules. And on each of the host molecules, there is a little hand sticking out that's made of acrylate. And they can react with each other. So the hand can hold another hand. And this needs light to shine UV. Okay. Basically, the idea of the gelation process is that you have these polymer chains, okay? And if you don't do anything to them, they are solution, okay? So they need cross-linking in order to become gel. So that's what we call a gelation process. And this gelation, this cross-linking is precisely provided by these hosts holding hands together. Because once you have such a complex with, let's say, 4 hosts, okay? And then each one of the hosts could bind to a guest from a different chain. And therefore you have realized the cross-linking, and that's when the gelation takes place. You would see a transition from a solution to a solid, a hydrogel as form.
So the green guys have only one thing, one.
Oh, no, this is the
Yes.
repeating unit. Yeah.
Oh, okay,
So-
I
so
see,
there are many, many of
Oh,
them.
yeah, I see.
Right.
Yeah, okay, got you.
So, right, so, and the setup is that you would throw in the cells when they were still the solution. And then you shine UV light, and then the gelation takes place. So that cells are basically locked in this hydrogel, okay? And next, what happens is that you can monitor how they develop, how they grow, okay?
Oh.
And what you found is that if you have the adamantane, the fast-on fast type, the cells develop this stellar shape, okay, in 18 hours, which is actually very fast. That is very rare in 3D medium. So you've seen them in 2D medium where they don't really have that much resistance on the surface, right? But in 3D, this is not commonly seen, okay? Whereas if you have the slow on, slow off guest, they would remain rounded, okay? They would remain spherical even after, I think, yeah, after 3 days, yeah. Okay, so if you mix the host and guest, if you mix the different guests together, you get graded behavior. So all of this is not entirely intuitive to explain from the point of thermodynamics, because I got this good question at BPS. Someone asked, like, what is the Young's modulus of these hydrogels? Are they different? And indeed, the Young's modulus are actually quite similar, okay? Because these type of bulk modulus tends to depend on thermodynamic rather than kinetic behaviors. So basically, how stiff, how tough your hydrogel is depends on how well you bind in terms of affinity, so KEQ, but not K on and K off. Okay, so how do we link the microscopic kinetic properties of the cross links with the 3D spreading behavior that we saw? So that's basically the question that we wanted to answer with MD simulations. So again, the setup, at least the initial one, is very straightforward. We are just thinking that why don't we cut the hydrogel, cut a little bit and simulate it and see what happens, right? So, so the first thing that we did is this type of spontaneous binding simulation where we don't actually form the host-guest pair from the beginning, we just let them bind themselves. And they're extremely fast. So basically they can bind themselves within hundreds of nanoseconds, which corresponds to the KEQ, which is 10 to the 8th. They're supposed to be really fast. Yeah. Okay. And then next what we did, so after they have all formed this pair, this cross-linking, so we said, all right, so what if we are the cell and we're trying to grow? Okay. And naturally what we do is that we want to exert a force on the environment. So now let's try to mimic that force and see how much damage or how much change we can do to the network. Okay, so we perform all these hundreds of very short simulations where we apply cellular level forces. So typically on the order of piconewtons, okay, tens of piconewtons, and see what changes we can induce in the network. So that's the idea. So what we found is that if the host-guest pairs happen to be in the bound state already, these piconewton level forces actually are very difficult to break them off. Okay, so you cannot easily break the bound host-guest molecules. So we tried actually a series of different forces, and out of these simulations, we only saw 2 events where the breaking occurs at the highest force of 102 piconewtons. So this is the rupture force of ADA and beta CD. So that's from atomic force microscopy. So you know that this is when they come off. So, right. So of course, a big drawback of this is that all of these simulations are nanoseconds. They're very short. Okay, but we can plug in the parameters, so including the rupture force and the known K on and off, okay, into a semi-empirical equation called Bell's equation that will allow us to estimate what will be the modified K off under such an external force, and then therefore deduce how long it would take for them to break off. And that would put us in the millisecond timescale. So still very, so later on I will talk about, whether that's long enough or not. Yeah, okay. So, but, all right, so the point from these simulations is that we can do control simulations where the host guest happens to be in the unbound or the free state. Okay, so the idea is that these are non-covalent binding. So you come on and then you would come off by yourself. So what if it is in the off state and the free state, or the free state, the cells are applying these forces? So how would they change, or what influence can they make? All right, so what we found is that if the guest happens to be already in the unbound state, then tiny amount of forces, piconewton forces, is actually sufficient to displace you, that is, move you out of the way. Okay, so the idea is that you come off, and with piconewton forces, we can move you away from your original partner, so that when the next binding events occurs, it will be more likely to be with a different partner, and therefore change the topology of the network. Okay, so all of this is basically
so these are the one with adamantane.
Yeah, these are very good question. So these are the ones with adamantane.
Okay.
So this is our first draft and submission actually. So the reviewers came back and said, you have 2 guests. So what about the other one? Yeah. So our initial reply was that fundamentally there should be no difference. So especially in this one, this is the fast one, and we cannot break them off. Right? So the slow one is actually only going to be harder. Yes, right. Right. So, but of course, yeah. So reviewer suggested we try, and we did try, and it turned out that the suggestion was very good. So it's good to listen to the reviewers. Okay, so I've learned that from another recent experience as well. So it's actually some of their suggestions can be very helpful. And in this particular case, it is particularly helpful because until we actually start to sit down and try to model the system, we would not have realized that our system is quite different from what we initially thought that we could borrow from the literature. Okay, so basically, like I said earlier, host-guest binding is very well established. There are tons of data that we can find from the literature, and in particular, it's the K-on, K-off of different host and guest pairs that we can find from the literature. So that's initially what we took for cholic acid as well. Okay, but later on, we realized that now that we're going to model the system, we have to really model its structure. And that's when we see that our cholic acid will have to be covalently linked to our hyaluronic acid chain from the carboxylic side. Okay, and this is its thin side. Okay, and it has a much bulkier head. Okay, so all of the literature values are actually about the K-on and K-off going in and out the host from this end. Okay, so whereas what we would need is actually the other end. So we don't have that data. Okay, so that's why we realized that the reviewer really helped us clarify that point, and that's when we realized that we have to do the work. So we basically, what we did is we ran about 10 microsecond ADF calculations to really figure out the free energy landscape of the binding. Okay, going in and out from the bulky head. And from this, we get to estimation. We get basically the delta G, okay, estimation of what how favorable this binding would be, and also the barrier height. Okay, so barrier height we needed because now we can combine it with what we learned from the literature and estimate the K off. Okay, so basically this is the story about the other guess. Okay, and then once we have that, we basically repeated what we did with the ADA. Okay, and we saw exactly what we expected. But still, it was very good. It was very nice that we were able to get this right by actually doing the extra simulations. Okay, so bottom line is what we learned from MD alone. Okay, is that if we just rely on the forces generated by the cell, which is typically on the order of say 10 piconewton, so a few piconewton, all right, it's actually difficult to modify the topology. So, right, so.
I have a quick question.
Yeah, of course.
The groups of hosts,
Yeah.
do you see them bonded to multiple different polymer chains typically, or can one chain be folded back around and have another one of its guests interact with the same cluster of
Yeah,
hosts?
definitely. So basically, yeah, so, okay, so not in our system because our hyaluronic acid piece is just too short.
Okay,
But in theory, there's nothing preventing, you know, another guest from the same, chain to fold back and
okay,
interact.
so the persistence length isn't too long to prevent that or anything like that?
No, right, you're right. These are very floppy.
Okay,
Mm.
thank you.
Sure. Right, okay, so, right, so, again, what MD can tell us is just, what I mentioned earlier, so you have a better chance, much better chance to modify or to promote the modification of the topology of the network if the host guest happens to be in the unbound state. Okay, then a natural sort of deduction that you can make from this process is that perhaps the faster the kinetics, the better it helps to enable the cells to modify the topology. Because the faster the K on K off, then the higher the chance that, or the more frequent that you will see these unbinding events. But we wanted a little bit more quantitative support. And like I said, MD systems is number one, limited to a single host guest complex. And number two, they are very short, nanosecond simulations. So in order to get a closer relation with experiments to really ask whether the data makes sense in terms of ADA and CA kinetics, whether they are actually fast or slow enough, or fast or slow relative to what. So we wanted to do a little bit more, and that's when we really dig into sort of the environment of the hydrogel a little bit more, and we thought what would be the correct reference scale to define what is fast or what is slow. Okay, so basically, based on our hydrogel network, we try to figure out what would be the barrier that a cell's actively growing cell would be facing in order to maintain its, spreading. Okay, so again, we went to the very initial, the very elementary step where a cell is trying to poke a little finger into its environment, which is made of bundles of actin filaments. Okay, so we ask, what about each actin polymerization event? So if I would like to add an additional monomer to grow this actin filament, how many of these host guest complexes would better be in the off state, in the free state simultaneously, so that I can grow unhindered? Okay, so that basically sets a natural timescale for us that answers the question of how fast is fast enough, because an actively polymerizing actin would typically have 100 monomers added per second, so that would put each event on the order of 10 milliseconds. Okay, so if we can be that fast, if the network or the host guest simultaneously can unbind at that rate, then we consider it to be fast enough. Okay, so the other thing is all of these parameters, all of the other parameters help us figure out how many of the host guests are actually blocking each actin polymerization event. Okay, so we estimated that up to 8 host guest complexes are facing each monomer, and they better be in the free state simultaneously. So how do we estimate that? So we turn to the so-called kinetic Monte Carlo. Okay, so we basically have to estimate, so we plug in the rates, the kinetic rates that we obtain from the literature as well as from MD simulations, and we basically ask how long would it, or how fast would it take, how long it would take, or how fast you can go into the off state. And we did 100,000 KMC calculations using the data that we obtained from MD, as well as some of the data from the literature. And indeed, this really allowed us to pinpoint or to pin down the effect of ADA versus CA, because we could see that precisely like the experiments saw, if we have a purely ADA environment, our gate, the so-called gate, so comprising of those up to 8 host gas complexes, would almost always open fast enough, okay? Whereas if we have Ca, okay, it would almost always be too slow. And if we have a mixture, then we have a graded behavior like the experiments. So to put everything together, so this is basically like this picture, this revolving door picture. So our actin polymerization is the person, or our actin monomer is the person arriving at the door. And the revolving door is made by up to 8 host gas complexes that will all need to simultaneously become off, okay? And if the door can revolve or open every time that a monomer, an actin monomer arrives at the door, then that polymerization can go nearly unhindered because you can add that monomer and then face the next door, okay? Whereas if this door is almost never opening fast enough, and every time a monomer comes to the door, it has to wait, then the polymerization is severely hindered, okay? So that's basically the first sort of hydrogel story, and I have a very quick, short second story that I should be able to finish soon, okay? So yeah, so this is another hydrogel system that we've started working on very recently, okay? So this is basically made by this PAA polymer, so polyacrylic acid. And what's interesting about this, so maybe I'll just show the movie, okay? So these are porcine heart, okay? So basically a pig heart, okay? So, and these are the hydrogels made from the sorry, I don't know if you can see, there is like this translucent hydrogel, okay? So on the left, we have, maybe I can try to say it again. So on the left, we have the conventional hydrogel, and on the right, we have the so-called DNR hydrogel. So as you can probably tell from the video, the right one has much better adhesiveness, okay? So this is actually on the wet part, okay? So basically, this is the desired wet adhesion performance that we want to achieve.
So this is something added to the heart, it's not from the heart.
No, not the
Okay,
heart. This is
just
the,
the stickiness, okay, I see.
right, so these are the materials. that we
Yeah, I
make.
see, I see, I
Right,
see,
right.
okay.
So the reason that we have that is because our hydrogel made from the DNR
Mhm,
method actually has hydrophobic surface.
mhm.
Okay, so this is perhaps not so impressive if you just, but it's actually quite strange because hydrogel almost by definition is hydrophilic.
Mhm.
Okay, so these are you have the little hydrophilic polymers, and then they would absorb water and then swell and then tend to be hydrophilic. Okay, but if we make them through this DNR method, we can achieve a hydrophobic surface. And this hydrophobic surface is actually not achieved because the mold, that is the thing that you use to hold the solution, so the mold surface, is not just because the mold surface itself is hydrophobic, because we can repeat the same manufacture process on different mold surfaces, ranging from hydrophilic to hydrophobic. And if we just have traditional mold, we would always end up with a hydrophilic surface, okay? So as indicated by these WCA or water contact angle. So what's the DNR then? The DNR is that we would graft or coat the mold with a layer of PDMS, which is hydrophobic polymer, okay? And basically we gave it the name dynamics-induced network reconfiguration, or DNR, because the requirement for this hydrogel to develop the hydrophobic surface is that the mold has to be hydrophobic and dynamic. Okay, so the grafted PDMS chain will have to have flexibility. Okay, otherwise, if you use traditional hydrophobic mold, then you lose this behavior. Okay, so again, to understand what happens, all right, so we did MD simulations, and then the first thing that we did is to try to model the assembly process. So this is basically a solution of the PAA polymers, and we basically model them on different mold and see, have first establish that they can assemble. Okay, and what we found is that on the PDMS or the silicon chain grafted mold, you can indeed see that a larger percentage of these polymers would like to form contact. And these polymers, so PA polymers, have their backbones that are hydrophobic. Okay, and they would arrange themselves and use their backbones to contact the surface. All right, and then if you have just the traditional glass surface, you would not have that. You would have mostly, or you would have a reduced percentage of the polar contact. Okay, so right, so basically, this is the first part. So we basically said use this to establish a baseline that there is a driving force due to hydrophobicity. And the next one, okay, so we want to study what is the effect of the dynamics. So this is the experimental result. So experimentally, you can cross-link this PDMS chains, and as you increase the cross-linking percentage, they become more and more rigid and less dynamic, and you lose the DNR effect, because once you make them completely rigid, you have nothing but an ordinary hydrophobic mode that does not support a hydrophobic hydrogel surface. Okay, so what we did then is we do exactly the same with MD simulations with exactly via restraints. Okay, so we can restrain different percentage of the surface and then see that, how they would impact each single chain diffusion. Okay, so with this, we basically want to establish that the dynamics actually matters to the surface chain rearrangement, because once you are in a hydrogel, you're not alone. You're not a single monomer that you can do whatever you want, because you are under polymerization reaction.
Yeah.
You're forming gel, and your hands are tied, literally. Yeah. So if you would like then try to do this type of rearrangement, then surface dynamics does matter. And this is just so this is basically the second step. So if we have a single chain diffuse on the surface, then I can see that the surface dynamics does matter. And the last step, the third step, is to use a special type of simulation. So basically, we again put a single chain, but this time not on the surface, but with one of its end initially held. And we would then put a cylindrical restraint that will allow it to move vertically, but not horizontally. And this is trying to mimic the effect of basically crowding or steric clash that we face in a bulk hydrogel. Okay, so now we're basically creating a scenario that mimics what a polymer chain reorganization would face if they're already in a hydrogel network. Okay, so now that you would like to get attached to the hydrophobic surface and then, orient yourself to have your hydrophobic face touching the mold surface. So you will have to, we would like to see how the dynamics matters, okay? So we ran hundreds of these simulations where we would just put the restraint that, you're not allowed to move horizontally, but you can freely move vertically. And then we measure how fast it is for you to finish the adhesion process, driven by the favorable hydrophobic contact. So after hundreds of simulations, we can indeed get an information of the time it would take for this adhesion to occur and compare quantitatively between the different systems. Okay, so the numbers are probably not important, but the 0%, 100% actually compares. You can clearly see the difference. The 0% one means that the fully flexible surface supports very fast adhesion. So the 50%, 100% does not have statistical significance in their difference, but that's actually what we saw in experiments as well. Okay, so so I'm done. Okay, so in summary, so I told you about two stories about hydrogels, and in both cases, combining MD and sometimes with other techniques, we try to understand the connection between the molecular level dynamics and the much larger length scale and longer time scale, right? So so we were getting started, and there are still a lot of things to do. So especially with the polymer part, there's a rich set of literatures and the rotation movement for polymers in the network. So so we'll definitely continue to work on this area. So with that, I was just going to mention that this is our collaborator and very productive experimentalist and my postdoc. And also, some of the work was done by Evan, the student, and these are the rest of my groups. And thank you for your time.
you very much, Yi, for
You're very welcome.
the nice presentation. I'm sorry again for the projector.
Please.
So, okay, so time for questions. Yes.
I just had a quick question about, so as I understood it, when you shine UV light is when the hydrogel starts forming.
Yes,
Is there a reverse process that you can basically add some sort of stimulant or something that then causes all of the cross-linking to be removed from the system?
that's a good question. Not this type that I know of.
Okay,
Yeah. But yeah, decoratable is definitely something. So you,
and then in the
Yeah.
simulations,
Yeah.
were you always saturating the basically that hand-to-hand connection that you were talking about, or did you like vary how many of the cross-linking events that were occurring to see like if the dynamics would change if you only had like one connection versus it would be saturated, which I think you said was 4, I believe, right?
okay, so, well, okay, so in the all atom MD simulations, except for the very first set where we let the host and guest spontaneously find each other. So, so later on, when we apply the forces, our focus is always just one
Okay,
pair.
okay.
Yeah, so it kind of like, yeah, so we are isolating one pair and to see, how much this pair is being affected by the force. But you're absolutely right. How would they be affected by the status of the other pairs? So the thing is, if you consider the hyaluronic acid chain as a string is not really taught in the other part.
Okay,
So, right, yeah, you have a lot of freedom.
okay, thank you.
Yeah.
I have a question about the
Yes.
number of hosts in the host complexes.
Yes.
Is there a way to vary that, or do you have an idea of how that would change the mechanical properties of hydrogel if you have, host complexes that have 8 sites rather than 4, for example, or 2
Right.
sites instead?
Right, that's a good question. Our collaborators did not try that, and our calculation basically tried 2 scenarios that we found from the simulation. So because in simulations, we saw that more typically up to 3 can come together, and very rarely 4 can come together, and then there's a big bunch of 2 hosts together. So we played out different scenarios in the KMC calculations. So
Okay.
if you have
Got
that, yeah, but if you have more, how would that alter the mechanical properties? That's a good question. Presumably, it might increase the mechanical strengths if you have more, effectively,
Yeah.
your knot is tighter, perhaps. But it's hard to know for sure, and it's hard to imagine they go to number 8, because they would be very sterically
Yes.
hindered, yeah.
So you're doing actually really uncharted territories as far as parameters are concerned. You have to develop parameters for many of these things.
Right.
How do you feel about that? Do you feel that
Right.
maybe things can be different if you use different sets of parameters, or?
Yeah, that's a great question. So for host and guest, we're actually blessed because this is a very well-studied chemical system. So we did not have to do really very little. We had to do parameterization because the host adamantane and cholic acid, cholesterol.
Right.
So we were really
And
blessed.
cyclodextrin, right? That was cyclodextrin.
Cyclodextrin, yeah, beta-cyclodextrin, those are already in the chart. We didn't even have to do CGNFF.
I see.
Hyaluronic acid, those are basically disaccharide repeats, and that's also char. Yeah,
Okay, I
the
see.
only thing perhaps we had to do a little bit is the little hand.
Yeah.
When they held together,
I see.
but that had the like very low penalty values, something like that.
So I have
Yeah.
another question, I mean, related. So how do you decide about, for example, how much you decorate the nanodiamond with hydroxy groups? This the percentage of.
Yeah, so that's basically the zeta potential calculation.
Oh, I see
Yeah,
that. one.
so
Okay,
basically, yeah, the hydroxyl and COO minus, the COO minus gives you the net charge,
Gotcha.
so we can, yeah.
Parameters of that, yeah. I
Right,
see.
right, yeah, but it's still a simplification because real nanodiamonds don't just have these 2 functional groups.
Yeah.
Yeah, they have
And they are
sp2
not
carbon.
exactly that shape either.
Yeah, no, of course not. Yeah, that's right, that's
Right.
right. The surface is actually pretty complicated.
Yeah.
Yeah.
Very interesting. Any other questions for you? No, if not, please let me thank. again, sorry.
Yeah, no worries, no worries.
It's still on, now that you don't.
Yes, if I may.
All right, so let's go back, so now you can go.